Good day, students. Welcome to part 2 of the mixed review series on limits. So let's go over the following review problems on limits. Problem 1. Um, let's find the limit as x approaches 4.9 from the right of the floor of 3x over 2. All right. So in this problem, we can see that we don't have any issues with direct substitution of this value that x is approaching into the function. So we can just go ahead and substitute it. So we're going to have the floor, our greatest integer of 3 times 4.9 from the right, that divided by 2. Okay, then simplifying further, we'll multiply 3 by 4.9. So we're going to have the floor of 14.7 divided by 2. All right, so what's the floor of 14.7? So what the greatest integer function does is it rounds it and a non-integer to the greatest integer that's less than that non-integer. Okay, it rounds integers to itself. So the greatest integer that's less than this non-integer is 14. So it basically rounds it down to 14 over 2, and 14 divided by 2 is 7. All right. Okay, let's take a look at question number 2. For problem 2, we are to find the vertical and horizontal asymptotes and then you're to verify your vertical asymptotes using limits. Okay, asymptotes using limits. And the function under consideration is f of x equals the square root of 8x to the 6th minus 4x to the 4th, and that entire expression divided by x to the 3rd minus 2x. All right, we're going to start out by looking for the horizontal asymptotes. So let's write down horizontal asymptotes. All right, so to find the horizontal asymptotes, we're going to let x go to plus n minus infinity. And any numerical value that it approaches, finite value it approaches, as it goes to plus or minus infinity, that will be a horizontal asymptote. Okay, so let's go ahead and start by heading to infinity. So we're going to find the limit as x approaches infinity of the square root of 8x to the 6th minus 4x to the 4th over x to the 3rd minus 2x. All right, so when you're looking at the limit at infinity, the leading term in the numerator and the denominator are what we're going to focus on, because the other terms don't go fast enough at infinity. So in the numerator, I'm going to focus my attention on 8x, the square root of 8x to the 6th. And in the denominator, the leading term is x to the 3rd, so that's where I'm going to focus my attention on. Okay, so at infinity, the only thing that's the count, limit as x approaches infinity, is going to be the square root of 8x to the 6th divided by x to the 3rd. Okay, and then when I take the square root of the numerator, I'm going to have the limit as x approaches infinity of square root of 8 times the absolute value of x to the 3rd. Anytime you take an even root, you add the absolute value component there over x to the 3rd. Okay. All right. Now this is going to become. Now when we're going to infinity, we know that this absolute value is going to attain a positive sign, right? So let me just show you the steps. limit as x approaches infinity. Root 8 can be reduced into 2 root 2 times this can be written as plus or minus x to the third over x to the third. Okay, don't be in a haste to cancel because you don't know what direction it is yet. So I'm going to write this as 2 root 2 times the limit as x approaches infinity. Since you're going to infinity, it's going to take the positive sign, okay? So it's going to be positive x to the third over x to the third. So what happens is entire limit becomes, this divides to 1, so it's going to become 2 root 2. That's your limit as x approaches infinity. So there goes one horizontal asymptote. All right. Is that it? Absolutely not. We need to check the limit as x approaches negative infinity. So, and you just see what we get, okay? Because you could have two distinct horizontal asymptotes. So I want to find the limit as x approaches negative infinity of x to the square root of 8x to the 6 minus 4x to the 4th over x to the third minus 2x. When you're going to negative infinity, it's the same procedure for polynomial functions. You focus on the terms with the highest degrees, the leading coefficients, or the leading terms. So this is the leading term in the numerator, leading term in the denominator. So that's what we're going to focus our attention on. All right, so let's extract them. And now this problem now becomes the limit as x approaches negative infinity of the square root of 8x to the 6th divided by x to the third. All right. So when we simplify it out, the same procedure, we're going to have limit as x approaches negative infinity. Now the square root of 8 is 2 root 2 times the square root of x to the 6 is going to be the absolute value of x to the, x to the third. Absolute value of x to the third over x to the third. Okay? All right, now what we're going to have next, let's use a constant property of limits. So you can factor out the constants because it's independent of where x is gone. So 2 root 2 of the limit as x approaches negative infinity of plus or minus x to the third over x to the third. Okay? Now since you're going to negative infinity, this absolute value is going to take the negative sign. So it'll be 2 root 2 times the limit as x approaches negative infinity of negative x to the third over x to the third. You see that this divides out to negative 1. So our limit is simply going to be 2 root 2 times negative 1, which equals to negative 2 root 2. Okay, so what does this tell us? It tells us we have two horizontal asymptotes. So the horizontal asymptotes are y is equal to negative 2 root 2 and y is equal to 2 root 2. All right, so there goes your horizontal asymptotes. Now, next thing we're asked to find, we're supposed to find the vertical asymptotes and use limits to verify the accuracy of our results. All right. So our vertical asymptotes are our infinite discontinuities. Okay. So let's rewrite the problem. So what we're looking for the vertical asymptotes now. Vertical asymptotes. So what we're going to do is make sure we eliminate the removable discontinuities first before we start to look for our infinite discontinuities, which are our vertical asymptotes. Okay, so the original problem we have the function f of x equals the square root of 8x to the 6th minus 4x to the 4th, and that divided by x to the third minus 2x. Okay, let's make sure that there are no removable discontinuities first. So we have to simplify the top as much as we can, see if it cancels out anything in the bottom. And then what's left in the denominator, we can set to 0 to look for our vertical asymptote. So in the top, we can factor the numerator. By all means, we can take out 4x to the 4th And then we're going to be left with 2x squared minus 1 in the numerator. And in the denominator, we also have to factor to see what can be cancelled out. So in the denominator, we can factor out x squared. So we have x squared times I'm sorry, we can factor out x, not x squared. So take out x, and then we're left with x squared minus 2. All right. All right, the numerator, if we root both of them, we're going to have the absolute value of the square root of 4 is 2. The absolute value of 2x squared times the square root of 2x squared minus 1 divided by x times x squared minus 2. Okay? Now, we can completely reduce this. This x can reduce this. It doesn't affect the sign anyway. So this becomes 2x, because this is x to the 1. And I can cancel this x with that, with one of those powers. So you subtract 1, you're left with just the absolute value of 2x times the square root of 2x squared minus 1 divided by x squared minus 2. So what does that tell us? It tells us that there is a removable discontinuity at x equals 0. We don't want to include that, okay? All right, now to find our vertical asymptotes, what we'll do is set the denominator to 0, and that's solve for x. So x squared is equal to 4. Take the square root of both sides, and then you have the absolute value of x is equal to 4. So this tells us that x is equal to plus or minus, I don't know where 4 came from. That's supposed to be 2. Square root of 2. So root 2, so plus or minus root 2. Okay, so these are our vertical asymptotes. So vertical asymptotes is x equals negative root 2 and x equals root 2. Okay, so let's verify that these are vertical asymptotes. If they're vertical asymptotes, then the limit as x approaches this value from either direction will be infinity. It will suffice to just focus on one direction, because if it approaches infinity or negative infinity from one direction, then that is automatically a vertical asymptote. Okay, so let's go ahead and do the test with limits. Test with limits. All right, so let's start with the first one. So with the first one, we're gonna find a limit as x approaches negative root 2 from, let's do from the right for both of them, okay? All right, so I want to focus on the reduced form of this problem. So let's see, let's take that piece right there. Absolute value of 2x times the square root of 2x squared minus 1 over x squared minus 2. Okay? All right, so let's simplify that. We're going to have 2 times negative root 2 from the right times the square root of 2 times negative root 2 squared minus 1. And this whole story divided by negative root 2 square, negative root 2 from the right square, minus 2. Okay? All right, so this is going to become negative 2 root 2 times the square root of negative root 2 squared is just 2. 2 times 2 is 4. 4 minus 1. Over in the denominator, you're going to have negative root 2 squared is just 2 from the right, minus 2. So what is that going to become? If we simplify it, we're going to have negative 2 root 2 times the square root of 3 divided by, this will become 0 from the right, a very small positive number. So that becomes negative 2 root 6. 0 from the right can be written as 1 over infinity, right? And then it becomes negative 2 root 6 times infinity, which equals negative infinity. So that automatically shows that this is a vertical asymptote because it approaches negative infinity as x approaches negative root 2. Okay. All right. So before we do the next part, just a real quick correction. There's absolute value here, so I need to put in the absolute value. We don't want to forget that. So absolute value. So when you take the absolute value of negative 2 root 2, that makes it positive, right? So let me just take that minus out of there. So it's actually infinity, not negative infinity. Let's see. Not infinity, so let's see. Hello? All right, so just take out a negative positive, so that goes to infinity. So we see that that's a vertical asymptote. If it goes to plus or minus infinity, that's sufficient to conclude that it's a vertical asymptote, all right? So let's go ahead and test a limit from the other direction, limit as x approaches root 2 from the right. We're testing the second vertical asymptote that we have to see if the function approaches infinity, okay? So the absolute value of 2x times the square root of 2x squared minus 1 over x squared minus 2. It's basically going to be exactly the same thing. The only difference here is that this will be positive instead. So this is, I could skip some steps, could go right here. It's going to be absolute value of 2 root 2 times the square root. You know what? Notice when you square negative root 2 or positive root 2 is the same thing, okay? So this is still going to be a 4 regardless of the sign, minus 1 over, in the denominator, if you square negative root 2 or positive root 2, you get the same value, which is 2, but we are approaching from the same direction, so it's a 2 from the right, minus 2, okay? You can go through the mechanics to verify that this is correct if you want. So it's going to become 2 root 2 times root 3, as we determined earlier, over 2 from the right minus 2 is a very small positive number, equals 2 root 6 over 0 from the right can be written as 1 over infinity. So this equals 2 from the 2 root 6 times infinity. When you multiply the numerator by the reciprocal of the denominator, so your final answer is going to be infinity. Okay? So since the limit as x approaches plus or minus root 2 of the function equals infinity, that implies that plus or minus root 2 are vertical asymptotes. Okay, this is basically what the definition of vertical asymptotes are using limits. If it approaches that particular value and the function goes to plus or minus infinity, then that is a vertical asymptote. In this case, they will go to infinity, which is sufficient. All right, let's take a look at question number 3. So for question 3, we are to find the approximate slope of the function f of x equals x squared. The approximate slope at x equals 2 by finding the average rate of change on 1, 3. Okay, in this case we're going to be using the secant line. All right, the secant line to approximate the slope. Okay, and then this is the A part, and then in the B part you're going to find the slope at x equals 2, or the instantaneous rate of change. Okay, so find the instantaneous rate of change at x equals 2. So in option B, we're going to be looking for a tangent line, of course, at that point, since the line is intersecting the curve at only one point. And the expectation is for you to find instantaneous rate of change using the limit definition of instantaneous rate of change f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay? Alright, so let's start with the a parts. Let's find the average rate of change. Average rate of change. Okay, average rate of change on 1 comma 3. You want to note that these are x values, okay? So I'm going to call this AB. These are x values, that's why they're in brackets, not in parentheses. So please do not call this x and y, that's inaccurate, okay? So average rate of change is basically delta f over delta x. And you can find that on an interval by computing f of b minus f of a divided by b minus a. Okay, this is how you find the average rate of change. In this example, f of x is equal to x squared. All right, so let's go ahead and do it. So b is 3, so f of 3 minus a is 1 minus f of 1 over 3 minus 1. All right, now we're going to input this independent values into our function. So we're going to have 3 squared minus 1 squared, 3 minus 1 is 2. So 3 squared is 9 minus 1 over 2. 9 minus 1 is 8. 8 over 2 equals 4. All right, so there goes the average rate of change. Basically, we're approximating the rate of change at x equals 2 on the interval, using the interval 1 to 3. So let's write down what our answer means. So approximate rate of change. Rate of change, same thing as slope, right? Or slope at x equals 2 of f of x is equal to 4. Okay, so this is an approximation. It could be a good approximation or a terrible one, but it's just a secant line, so it gives us a general idea. All right, so for B, we would need to find the instantaneous rate of change now. So instantaneous rate of change. We don't need an interval because at an instant, all we need is a point. So at x equals 2 in this case. Okay, so instantaneous rate of change is df dx, which is the same as f prime of x, and is the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, in this problem, we know that f of x is equal to x squared. All right, so let's go ahead and do this. So inputting f of x into this situation, x squared, this is going to become the limit as x approaches 0 of x plus h squared minus x squared over h. Okay, now this will give us the equation for, or the function for the rate of change at any x value. Then when we're done with this whole procedure, we're going to pin our rate of change to x equals 2 by plugging in 2 into the resulting function, okay? All right, let's simplify this. We're going to have the limit as x approaches 0. If you expand this component, you have x squared plus 2x h plus h squared minus x squared over h. Now the x squares cancel out. So this is going to become a limit as x approaches 0 of, we can factor out the h, right? Of h times 2x plus h over h, okay? Now, you can see why we didn't bother plugging in 0 for h from the onset, because we would have had a 0 in the denominator, which is we can actually evaluate. So we have to simplify it as much as we can and remove removable discontinuities. As we can see here that h equals 0 is a removable discontinuity. So let's go ahead and take that out. Take out h. So now we're going to have the limit as x approaches 0 of 2x plus h. We can now input h into our function without any complications. So we have 2x plus 0, which is just 2x. So this tells me that the function that represents the instantaneous rate of change of the original function, f of x is equal to x squared, is 2x. Okay, so this is f prime of x. All right, so now we have to pin it at the specified x value. We have to find the instantaneous rate of change at x equals 2. So we're going to evaluate f prime of 2 by inputting 2 into our function. 2 times 2 equals 4. So the instantaneous rate of change of the function f of x equals x squared at x equals 2 is equal to 4. Okay, this is a coincidence. In this case, the approximate and the instantaneous rate of change are the same. So this is a perfect approximation. But it's not always the case, okay? So this is just coincidence. So don't always expect that the slope of the secant line matches the slope of the tangent line. This is just a coincidence. In some cases, that's the case. In other cases, the approximation is terrible, but the instantaneous rate of change tells you exactly what the slope is at the particular point. All right, so there you have it. All right, let's take a look at question number 4. So question 4. You're to use the limit test. Use the limit test to determine if the given function, function is continuous at x equals 0. Okay, and the function is a piecewise defined function given by f of x equals sine x over x when x is less than 0. Function is equal to 1 when x is equal to 0. And sorry about this, I'm going to try this well. And the function is x to the 4th plus x to the 3rd over x to the 3rd when x is greater than 0. All right, so this is the piecewise defined function that we're going to be focusing on in this problem. All right, so let's go ahead and start testing. Okay, so let's start from test number 1. So test I. We have to show that the function is defined at the specified x value. Okay, so that's we have to show that f of 0 exists. Okay, because we have to prove continuity at x equals 0. So we have to, part 1, test number 1, we have to show that the function is defined at that specified value. So what is f of 0 in this function? In this function, f of 0 is clearly 1. So we see that it is defined in this piecewise defined function. All right, test 2. For test 2, we have to show that the limit as x approaches the specified value 0 of the function exists. Okay, we have a piecewise defined function here. So we're going to be using 2 different functions as we approach the specified x value from both directions. So let's draw a number line to order our functions. So the specified value that we're going to be approaching is 0. To the left of 0, less than 0, this is the function that's active. To the right of 0, this is the function that's active. All right, so we have to evaluate the left and right hand limits. All right, so let's start with the left hand. All right, left hand. Okay, so the limit as x approaches 0 from the left of the function is the same thing as the limit as x approaches 0 from the left of sine x over x. And using the squeeze theorem, we know that this is equal to 1. All right? So let's find the right-hand limit. If they're both the same, then we can conclude that the limit, in fact, exists. All right? So the right hand. All right, so for the right hand, we have to show that the limit as we have to find the limit as x approaches 0 from the right of the function. And that's the same thing as the limit as x approaches 0 from the right of x to the fourth plus x to the third over x to the third. We can see here that if we plug in 0, we'll have some complications, and the denominator will have 0 there, and we can divide by 0. So let's go ahead and factor the numerator and then reduce. Okay, so limit as x approaches 0 from the right, factor out x to the third, so you're left with x plus 1 over x to the third. And what you see happening here is some cancellation action. This cancels with that. So this limit becomes the limit as x approaches 0 from the right of x plus 1. And then when you plug in 0, it's just going to become 0 from the right plus 1, which is just 1. Alright, so since the left and the right hand limits are the same, we can conclude that the limit does exist. Okay, so since the limit as x approaches 0 from the left of the function is equal to 1, and that is equal to the limit as x approaches 0 from the right of the function, that implies that the limit as x approaches 0 of the function exists. So this function passes test number 2. All right, so test number 3, last but not the least, test 3, we have to show that the limit as x approaches the specified value 0 of the function that we just determined in step 2 is equal to the value of the function at a specified x value f of 0 as determined in part 1, in test 1. So is that the case? Absolutely. Because we just determined that the limit as x approaches 0 of the function, the left and right hand limits are 1, so the double-sided limit is 1. And that is also exactly what the value of the function is in test number 1. Okay, so it passes test 3. So what's our conclusion? The conclusion is that the function is continuous at x equals 0. All right, so there you have it. All right, let's take a look at the last one, problem number 5. So for problem 5, we're to find the value of a that makes f of x continuous. Okay, so what on earth is f of x? So let's write down what f of x is. F of x is the piecewise defined function given by ax plus 5 when x is less than or equal to 2, and x squared plus 5 when x is greater than 2. All right, so the question is, what value of a will ensure that this function is continuous? So the function is continuous. We know that the left and right hand limits is going to be the same, and since 2 is included in the left hand function, then that also covers the whole idea of the function being defined at that value. Okay, so let's do it. So all you simply do is you're going to plug in this value into these two functions and set them equal to each other. Okay, so we're going to do, let's see, a times 2 plus 5. It has to be equal to 2 squared plus 5. Okay, so what did I just do? I substituted 2 into, let me show you some arrows. Take this 2, and I input it into the function to the left, and then this 2 into the function that on the right. So I'm trying to force them to be the same, okay? All right, so that will make it happen. So let's solve this resulting equation for a. So we're going to have 2a plus 5 equals 2 squared is 4, 4 plus 5. that yields 2a plus 5 equals 9. You can subtract 5 from both sides. You have 2a equals 4. 2a equals 4. Divide both sides by 2 and you end up with a equals 2. So this value will make the function to be continuous. But thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel by clicking down the subscribe button. You can post the comments to let me know what you think about this tutorial. You can like it or share it via your individual social networking program. More clips like this can be found at webserve.com/calculus, or just scan this QR code for direct access to a whole collection of calculus tutorials such as this. Thanks again for watching and have a wonderful day.